Good morning. Thank you for being here on a busy day and a busy week. I know you guys have a review tonight for the plant biology exam, and the exam is Friday night. So I know you're a bit preoccupied with all of that material. So thanks again for showing up. The object that's getting passed around, try to figure out what that thing is. Please be careful holding it. Don't drop it. And it can gradually make its way to the front. We'll talk about it soon. My name is Alan Schabel. I have taught Bio 1B for several cycles now. I don't do the evolution section that often in the regular semester, but I do enjoy it, and I'm looking forward to, 13 lectures with you guys. And I'll talk more about my own research later in the series. I'll have some time toward the end to talk about my work on African mammals and the evolution and ecology of African mammals. Lectures are in here, as you guys are well aware, at this time slot now, at this point. My office hours will also follow lectures, as did Dr. Feldman's previously, I believe, on Monday and Wednesday, 9 o'clock for an hour. In the same room, 5045 upstairs. I can't meet on Fridays. I'm on field trips on Fridays with another class, but I can meet by appointment. If you email me, we can set up a meeting outside of that regular time slot. And the dates of your evolution exams are up there. You'll have a midterm, and you'll have the final, a cumulative final that will include questions from all three sections at the end of the course. Stuff you guys probably know already. So I'm talking today about the history of the concept of evolution. It has a long history in the history of ideas, and we'll stretch it back as far as we can in human evolutionary history. The concept of evolution is controversial in some parts of the world, and we want to know the whole rich history of how we've arrived at where we are today in order to best understand it. So we'll look at about 40,000 years of history in, 50 minutes, 45 minutes here. So we'll be doing things with a broad brush in portraying this history, but hopefully it'll give you some grounding in how we've arrived. On Friday, we'll continue that series in the history of evolutionary ideas with Darwin's discoveries. And then we'll move into really modern biology in the third lecture. We'll start today by looking at our species and its interaction with the natural world based on some archaeological insights from Europe and around the world. Then we'll look at the earliest ideas in Western thinking on evolution itself, the concept of a universal history or a history of life. And then we'll gradually home in on the time around Darwin and the time leading up to Darwin in order to look at the ideas that specifically influenced Darwin. We'll look at adaptation as a phenomenon that is intelligible outside of an evolutionary context, and then how the concept of adaptation is reformulated in an evolutionary context. And hopefully I'll finish by discussing the concepts of homology and analogy, critical concepts to understand as we move through this section. Concepts you've already been introduced to in the previous section with Dr. Feldman. So sometimes I'll reiterate things that Dr. Feldman already discussed. Other times I'll elaborate on some things he discussed. Some things will be completely new. By way of introduction, let's look at this place in southern France, a place called Chauvet. Chauvet Cave was discovered in the mid-1990s and quickly became well known because of a really impressive array of paintings inside this cave system. Now, these caves have been looked for over the millennia by people in Europe, and many caves have been discovered like that. You may have heard of Lascaux or caves in Spain that have artwork on the walls. Well, this one, these cave seekers, these spelunkers, as they're called, the name for someone who's out looking for caves is a spelunker. Well, these spelunkers are moving along these cave walls and literally trying to feel for drafts of air coming out of the rock, putting their cheeks to the rock to feel little drafts of air that might indicate a larger chamber inside the rock that they could explore. And that's what this small group found, was a small point of access into the rock that ended up opening up into these large galleries. There were bones inside the cave as well, fossil bones. And there were marks on the walls made by torches that people had carried with charcoal, with carbon in the torch residue that could be dated very accurately by radiocarbon dating, carbon-14 dating, which provides a really precise and accurate estimate of the age of the cave. And it was estimated to be 32,000 years old. That notation there, just Ka. Let's see. Here, that'll work. So this notation, thousands of years, kilo ani. I'll use other similar abbreviations for age. But 32,000 years ago, if you can try to conceive of that span of time. So what did they see in the cave once access was granted to cameras and investigators? Panels like this on the wall, paintings, drawings, sketches, artistry from 32,000 years ago. And those are clearly horses, right? You can see the horse. You can see the long face. You can see the mane on top, small eyes. Even the eyes look like good horse eyes. These are faithful renderings of the animals that these people must have seen that long ago. Now, it's not a horsey like you have in the barnyard today, one of these tall, really tall, fast, domestic breeds of horse. This is something more akin to zebras or some relative of horses and zebras. It's an equid. It's a horse. But what kind of horse? Well, that's for scientists to work on based on all available evidence, including fossil bones that would be found in the cave, but maybe even these depictions on the walls, because there's evidence in these depictions. There are data in these paintings. Large panels like this, if there were a person in this depiction, they'd probably stand this high or something. So these are large panels. And this one includes rhinoceroses and various felines. So rhinos roaming around the Western European landscape with people at this time period. An image like that. And what is that? It's a bear, right? Just a few lines and you recognize a bear with the little ears and the short muzzle. The expression, I mean, there's no eye there even. There's just a couple lines. It's incredibly artful. It's a beautiful painting. It turned things upside down for the archaeologists because art was supposed to progress. Artists were supposed to get better and better over time. But the next most recent cave sites that were known at this time were Lascaux and the others from 15,000 years ago. And it's subjective, art criticism, of course. But in my opinion and some others, they were less beautiful, less faithful renderings of the natural history of the landscapes. They were more symbolic. They were more culturally symbolic and less naturally historic. And these are capturing something about the animals, the people in very close relationship with the creatures that they lived with. And a bear was an important member of that community. In fact, it's a cave bear. There's the Latin Ursus spelaeus. The genus Ursus is the bear genus. Our mascot, right, for Cal Berkeley is a grizzly bear. A grizzly bear is on the seal of California. We don't have grizzly bears in California anymore. They've all been shot out. But that's genus Ursus also. Ursus arctos. in the case of the brown bear or grizzly bear. This is another species of bear, Ursus spelaeus. And there's your root for the cave, just like spelunker, spelaeus. Ursus spelaeus, genus, specific epithet, right? Capitalize the genus, lowercase on the species, underline it if you're writing it, italicize it if you're on a computer. That's the Latin binomen for a cave bear. It's a relatively vegetarian bear, big thing, that coexisted with humans in Europe. What are those? Somebody said mountain lions. That's excellent. Not mountain lions specifically, because they only live in the New World. They only live in the Americas. But a lion, yes, a cat. Indeed, it's thought to be very closely related to the living African lion. So closely related, you might estimate that it deserves only subspecific ranking. Not full species, but subspecies. Panthera leo, the species of African lion, and Panthera leo spelaea, the subspecies of lion that is represented by the cave lions of Europe. So it's a subspecies of the larger Old World lion species that also includes the African lion. So you might add a subspecific name to the Latin name to identify this creature. And the paintings actually reveal information about this organism that we didn't have before. Lions are well known to hunt in packs, right? Today, it's mostly the females that lead the hunt. And you don't see a maned male lion in the front of a pack of hunting lions. It tends to be a group of females. The males participate more or less, but they don't lead the hunts. But here, in this case, you have a male in front of a female. The male's larger. The male, as illustrated here, the same painting illustrated here, you can see the testicles on the back. You know it's a male. It's larger, and it has testicles. It's a male. Given how closely these artists have represented the creatures, you can take that literally. It's a male lion and a female lion. Well, a couple things to note. The male doesn't have a mane. We would never know that from fossils. But probably the male lions of this subspecies didn't have manes. It's a curiosity. No one's going to get rich from that discovery, or famous even. But it's a neat natural history curiosity about this group of lions. And also the males seeming to participate in the hunt, because this is a hunting formation where these things are pursuing bison in other depictions on these cave walls. You can actually learn biological information from these paintings. It's extraordinary. Now, since that time, other sites have been discovered that are equally old or older than Chauvet, including just recently a site in Indonesia at 40,000 or so. It depicts a babirusa, this relative of pigs with these curious teeth. And so these, on your PDFs that you have on B courses, and they're up now on B courses for this first lecture, these information buttons, if you want more information, you can click them. If they're green, they're just for fun. You can click them and read them if you want. I may put some required readings up in red buttons, and I'll draw attention to them in lecture too if I want you to certainly read something. But otherwise, they're just clickable for fun. On that note, your book readings that I've assigned are recommended readings. For my section, like the previous section, I believe, they're not required readings. You won't be examined on material that's only in the textbook. It's just meant to supplement what's in lecture. So other sites, including Spanish sites, Indonesian sites, and Australian sites that also have ancient artwork, if this stuff tickles your fancy. So let's jump ahead some tens of thousands of years to the Greco-Roman thought. Now these are the earliest records of written history, right? And some of the writings of even these old characters don't survive as writings. They survive in the writings of later philosophers who wrote about their predecessors. Now, the writings of an Anaximander themselves don't survive, but the writings of Aristotle or Plato do, and they may have written about Anaximander, for example. And, this is not critical for your exam. This is just to build our background here. You don't need to know these names on this slide, these guys, but just recognize that these guys were wrestling with the concept of a universal history, a history of the planet and a history of the universe. Anaximander and Empedocles, they had a notion of the earth and the universe forming out of a chaos, and everything that we see today, all the complexity we see today, arising out of a unformed sort of chaotic medium. Empedocles was the one that gave us the notion of elements: earth, wind, air, and fire. So he established these physical categories of solidity, fluidity, and gaseousness, the plasma of fire, as a dividing physics for the universe, and that was very influential. And he spoke of the origin of life as having had a moment in time, a moment in history. The poem of Lucretius on nature, De Rerum Naturae, is well known, and you can Google it and read it if you want. It's really sophisticated. It's a sophisticated portrayal of universal history. But none of this is in the modern concept of evolution. This is all just the underpinnings, the ideas of a history itself. Aristotle, now he's someone you should know as part of this section. I mean, he really influenced biology for the next 2,000 years. He was a very sophisticated biologist. He would spend summer times dissecting organisms on the coast at his coastal home. He knew anatomy extremely well. He was a philosopher, yes, but he was practically grounded in the material world. That's what this painting is meant to depict. That's Aristotle on the right, on your right, and Plato on the left. Aristotle has his hand gesturing toward earth. Plato gesturing to the heavens or to the sky. Plato, the philosopher of ideas and archetypes. Aristotle, more grounded here in the material world and the study of nature, as a contrasting but integrative approach to the world, these two. Here in the same academy, Aristotle joined Plato's academy. They were contemporaries. Really fascinating. They both understood nature to be a hierarchy. The notion of a universal hierarchy, or a scale of nature, or a great chain of being, was one that they adhered to, and one that most everyone after them who looked in depth at the natural world adhered to. That nature was somehow organized in a great hierarchy. From the material world at the bottom through the lowest organisms, and this would start with like mosses, and then higher plants, and then insects and invertebrates and lower vertebrates, all culminating in human beings and angelic forms, and beyond that in these theological depictions. But, I mean, you recognize, and it even influences our terminology today, right? You guys have probably been talking about lower plants and higher plants in the first section of the class. That stems back to this, the concept of the mosses, the bryophytes, for example, being lower on the chain. Your noble flowering plants being higher plants. So you should delve into your own metaphysic in how you're relating to organisms, because this stuff is still in our culture. These old ideas still influence how we think about the world. And the great chain of being permeates cross-culturally notions of universal hierarchy. Now, continuing the history through the Middle Ages, after Aristotle being, 2,000 years ago, more than that even, you had this long period where there was very little, correct me if I'm wrong, but very little major biological advancements. Very few major biological advancements. and the so-called Dark Ages or Middle Ages. I've looked into it a bit. I'm no historian, but I've looked into it a bit, and you don't find much. You find good medical advances. You find some good advances in anatomy, but it was a pretty quiet time for creative insights, creative scientific insights. If you wanted to know something about biology, well, you took Aristotle's book off the shelf and you read about it. You didn't go look into the horse's mouth yourself. You read what Aristotle had to say about horse teeth. So, but I would love to hear from you if you have other counterexamples. We also have a poor history from the non-Western world in a history of biology, in our histories of biology, partly through lack of translation of other sources, what was happening in North Africa, in the Middle East, in India, in East Asia, a lot. Were they contributing to the larger stream of evolutionary thinking? Well, not so much, only because Western Europe was insulated from those influences, largely. And we still are, in our teachings here in California, insulated from some of that history. So it does need to be enriched. That object that's moving around, has it survived? Have it here? Excellent. So this thing. So these types of things, sorry it didn't make it to the back, but it's this thing here. Oh, it's awfully warm now. Jeez, this thing holds heat, picks up heat. It's hot. This thing is hot right now. This object, I don't know if you can see it, but it's this object. It's one of these. And these things were found around Europe. You can find them in America, specifically in the southeastern U.S. They've always struck a chord with me because my mom's sister, my aunt, had one of these on her wall in her home that she had found as a young girl. And these things were well known to people in Europe, as they are today. But they weren't known, it wasn't known what they were. They were called tongue stones. They kind of looked like a tongue, maybe. So they were called tongue stones. And it was generally thought that they just grew in the soil or fell from the sky and were embedded in the soil, having fallen from the sky. A popular notion was that they broke off the moon and landed in the earth. And so you find one, it's fantastic. It's magical. Wow. There's a glossopterae or something, what they called them. It came from the moon. Certainly I'm going to keep that. You put it in your pocket until it breaks in a few years and turns to dust, and hopefully you find another one. I'm glad it survived moving around the room. So the notion of what this thing represented was late in coming. And it wasn't until this genius Steno was sent the head of a shark that fishermen had caught on the banks of the Mediterranean. So these guys had hauled in a big shark. They hadn't seen a shark, maybe of this size or of this type, before, these fishermen. And they knew that Steno was working somewhere in Italy. And they said, we got to send this thing to Steno, because everyone knew that Steno was this anatomical genius. So they cut its head off, and they sent the head of the shark. You can imagine the condition it must have arrived in when it arrived in Rome or wherever he was. And Steno examined that shark head, did an anatomical dissection. One of the first things he realized was that the teeth in that big shark resembled more or less exactly the tongue stones, right down to the little serrations on the edges and the sides of the teeth. If you rub your finger along it, you can feel click, 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 click. They're serrated. Just like T-Rex's teeth are serrated. It's typical for these large sharks to have that kind of an edge. So he made the connection. Someone else had done it 50 years earlier. There's always a precursor. Some other Italian had written about that speculative notion that these things actually represent a once living organism. But Steno provided the solid evidence to convince people that this represented a once living shark. And it's found in the earth because it fell out of a shark's mouth and became fossilized in the earth. The components of it might have changed. Steno even speculated on the replacement of the material of that original tooth by other materials from the environment, but the form of it is maintained. in the form of the shark's tooth or tongue stone. So see how this is one of the earliest recognitions of an ancient life, that the world predates what we see here on the landscape now, and that there is ancient life that's influencing contemporary life. Even more influential, maybe, than Steno's recognition of a fossil and the existence of a fossil was his geological recognition of the law of superposition. So this Steno was not just an anatomist, but he was a geologist. He was a bishop. He was a Catholic bishop. So he was very much ensconced in the church during his scientific work. And one thing he recognized geologically was the difference in strata, the stratification of geological layers as you move up a hillside like this one. See how these red beds down here, these red or pink beds, are overlain by this white band, and above that you have a bed of different composition with the forest growing on top of that? Well, Steno recognized that these strata actually have temporal significance, a significance about timing, with the lower strata representing an older time, with the movement upward representing a movement through time toward the present. This law of superpositioning. If something is superpositioned, if it's on top of another thing, it's younger. And the thing lower down in section is older. So what if you find tungstones here and tungstones here, and they differ in their form, in the way they look? Well, the ones here are older than these here that must be younger. So you start to get a timing influence here. You start to get a recognition of relative time to relate to your fossils that you might find. Huge insights from the 1600s. He's working in the 1660s on this stuff. That's old school. Now, this is also a time of global exploration, which is going to continue for the next 100, 200 years. This age of discovery, this long age of discovery. Two more figures here that are not critical to know the names of. You never need to know the dates of these people except in a relative sense. You need to know that Aristotle's really old. Steno's relatively old. Darwin follows all of that stuff. That kind of relative timing, but certainly not birth and death dates. I'll draw up a term list that'll help you identify exactly which points are critical on these things. This is just to show a couple of these major figures in this age of discovery. James Cook is credited with being the first European to get to Australia, New Zealand. People like Cook were traveling the world largely for militaristic mapping purposes for the governments that they represented. But they often took naturalists, people like Banks, the great botanist Banks, on their trips with them. Banks would go out and collect eucalyptus trees while Cook was navigating the shorelines, and people like Banks were collecting specimens and bringing them back for scientific study. Tremendously important collection efforts that would influence thinking back in the home countries regarding biology and, in our context, evolutionary theory. So everything here is in the context of more and more specimens accumulating in museums and cabinets of curiosities. The upper classes in these times would often keep cabinets of curiosities in their house. They'd have it's your kitschy stuff, I guess. It's your shelf of baubles. But in their case, it would be natural objects that they would keep that would be found on the landscape or purchased at market from different parts of the world. A unique bird feather, an interesting shell. People were interested in these kinds of curiosities. With that accumulation of specimens in museums and curiosities in homes, there needed to be a system for organizing all this stuff. And that's where Linnaeus made such a major contribution. in providing a nomenclature for organizing these curiosities. We already looked at the binomen of genus and species, right? Well, he had the whole hierarchy of ranks from kingdom and phylum down to genus and species. That was extremely useful for organizing information. It's also, in some ways, now bankrupt, that whole hierarchy of namings and rankings. And we'll talk about that as the section moves on. But in many ways, biology is moving away entirely from the Linnaean ranking system in terms of the formal ranks, kingdom, phylum, and so forth. So we'll focus on that when we get to our lectures on phylogenetic systematics, and it's a really fascinating revolution that's been happening over the last 20 or 30 years in biology. But Linnaeus' contributions were real. He was working in a natural theological context, so he was inspired to study the world because it represented a reflection of the mind of the creator of the world. He saw organization in the world that reflected the organization in the creator's mind. So it was a theological pursuit, his biological work. He was interested in the origin of species. Linnaeus was interested in hybridization and the sense in which hybrids could represent new types of organism. But he wasn't an evolutionary thinker at all. The notion of this is where you get set up the debate between creationism and evolution in this time period. And people like Linnaeus and Paley less of a biologist, more of a philosopher, but they could study nature and study organisms without adhering to an evolutionary theory, of course. Could perform great science without an evolutionary background. But soon the evidence will accumulate and the ideas will circulate and congeal into a formal evolutionary theory that explains so much of the evidence. Soon meaning right after Paley's death in the 1800s. Paley made the argument from design for an argument for a created universe, because these evolutionary ideas are starting to circulate around this time, around 1800 particularly. But Paley reasoned that if you're walking across the landscape outside, say you walk across campus, and you find a watch on the ground, you find a smartwatch on the ground, you don't think that that smartwatch grew out of the earth or fell from the sky. You think this thing is crazy unique, it's functional, you open it up and you see all the parts, you see the chips inside, and you think, someone created this. Someone designed this, conceived this, and made this thing. There was a creator for this object because it's just too complex and functionally interconnected to have grown by itself. So it had a creator. You make that argument for the watch. He says that if you're walking and you kick a stone, you wouldn't need to make the argument because the stone is too simple. There's no functional integration in the stone. There's no connection to the rest of the world that's clear. It's just a stone. But if you look at an organism like a plant or an insect and dissect it, you see all that complexity and that functional integration. It too must have had a creator. So there's a leap from the human artifice to the natural world that makes the argument for a creator. And that's largely the argument that was made right up till Darwin's time. Darwin, if you were studying biology in the 1800s, you would have had Paley's book as part of your studies. You would have read the argument from design in your approach to the natural world. And in adhering to that, you can study the natural world in all its complexity. And you can recognize adaptations in the natural world as having been established by a creator to benefit those organisms. So the frog with its long legs sitting on the bank, ready to escape the snake by leaping into the water, has long legs to jump away from the snake, to land in the pond, and then swim with its webbed feet to get away from the snake, because a beneficent creator gave that frog those properties in order to survive in the world. The form of the frog fits its function. The long legs fit its jumping ability. The webbed feet fit its swimming ability. The complexities to see and to look at in relation to natural history and biology. All the birds here on these slides are present in Berkeley. Osprey down in the marina with their giant talons, right? Big osprey with these huge talons for catching fish. And I guarantee you there's a osprey hunting in the East Bay somewhere right now. Loons do well in the Bay Area. Loons, this big heavy bird with the feet on the back of the body. You can see the shadow of the feet right in here. The feet are positioned way back on the body because it's a big diving bird, big heavy diving bird with this dagger bill. So it dives underwater deeply to catch fish. These are adaptations. These are aspects of the form of this organism that aid it in pursuing fish and the lifestyle that it has. Now, we'll wrestle with some of these arguments. Here's a baby loon riding on the back of the mother loon. The back of the mother loon is flat like that. Well, is it flat in order to hold its babies on top? Do you explain every feature of this organism as perfected for some function? You'll need to think about that when you're in labs and looking at organisms. You'll ask, what is this for? You'll ask some part of an insect, some part of an organism. You'll ask your GSI, well, what is this for on the organism? That's our natural tendency to ask, what is it for? So if you find yourself doing that, ask yourself, why are you asking, what is it for? Does it have to be for something, every feature of an organism? What is your nose for? Well, it's for smelling. Is it for holding up your glasses? How do you answer the question of what are all these things for? These are important. These are actually very important things in getting after our evolutionary theory of organisms. Terns, gulls. Gulls, most people have a relatively fraught relationship with gulls, but they're actually fascinating birds. Great omnivores with that Swiss Army knife of a bill. Yeah, they can steal your hamburger, but they're also really well equipped for lots of aspects of life on the shorelines. There's multiple species of gull here in Berkeley. Yellowlegs you can see wading around with the long legs, good for wading in the shallows. The long bill for probing in the mud and sand. Oyster catchers, one of my favorites, that slips its bill, its narrowed bill, into oysters and mussels and snips the adductor muscle in the bivalve before it closes, and then the shell opens and then it eats the meat from the mollusk. These things hunt down at the Berkeley Marina. At dusk, you can sometimes see groups of them down at the Berkeley Marina. Great bird. And so forth. A few more historical points before I finish up. And this guy was a big influence on Darwin. This guy was a big influence on many people. He was a very celebrated naturalist, a German naturalist who traveled in the Americas extensively. A great traveler, great voyager. There are more places in the world said to be named after Humboldt than anyone else. So our Humboldt County, California, that's named after Humboldt. Many other Humboldts around the world, in the Caribbean, in South America, all over the place. He was really interested in politics, social betterment of underrepresented peoples, but he was a great botanist, naturalist, early ecologist, a really interesting person. And he traveled to the New World and specifically made these trips up the Andes Mountain, navigating up the Andes, carrying really nice instruments, the best instruments of the day, German-made fine instruments to document temperature and pressure changes as he ascended these mountains and looked at the plant communities and identified changes in communities as he moved up in elevation. So he mapped physical features in relation to biotic features and made correlations between the two. And that's ecology at its root. And so he had this great influence in that regard, but also just on these trips. He would get home and there would be parades for Humboldt, in Europe, and he'd go to city and tell about his adventures, and he wrote books on his adventures, and he inspired a lot of young people to try to do the same thing. And Darwin caught that bug and tried to follow in the steps of Humboldt in his own travels. Geologically and philosophically, big influences from this time were Hutton and Lyell, and the concepts of gradualism and uniformitarianism. Hutton advanced this notion of slow, incremental geological change, leading to great, big geological changes. For example, a small stream turning into a small creek and a small river that grain by grain excises a whole canyon in the landscape over time. Given enough time, grain by grain, you could form a Grand Canyon from the flow of a trickle of water. Very small changes leading to these vast changes, if you have enough time to realize those big changes. That's gradualism. That's a gradualistic philosophy, against a philosophy of catastrophic, massive, fast changes, for example, which were more the way that things were conceived to happen on a grand scale. Fast, explosive, like big floods, big impacts, big explosions. You can set Hutton against those notions in his gradualism. Lyell, a geologist and a writer, a lawyer, picked up some of those older ideas of Hutton, moved them forward, and also argued the concept of what came to be called the concept of uniformitarianism. And this is a really important notion for all of science. It's the notion for physics, for astronomy, for biology. It's the notion that the laws we see acting today must have applied in the past. And we can't assume new laws or different laws in the past if we don't see them acting today. It was, in part, an argument against miraculous explanations of past history, because miraculous explanations tend not to be visible today. And if they're not visible today, then we can't use them as explanations for past events. That's the uniformitarian assumption, and it undergirds science. And Lyell argued it persuasively. The lawyer that he was, he argued it well, and he used geological evidence also in framing his ideas. One more guy here to introduce two more before we get to Darwin next time. Cuvier, who established paleontology and the study of fossils as a legitimate enterprise. Working in Paris on fossils of the Paris Basin, he showed that there were forms that lived in the past that no longer lived today. The shark of Steno. Well, Steno didn't suggest that the tungstones represented a shark that's no longer on Earth. It was somewhere on Earth, we just didn't know about it. Cuvier suggested for the first time that the animals he was finding as fossils no longer exist anywhere. They went extinct. The whole notion of extinction was a new one, and people didn't agree with it at all right away. Because in that great chain of being, you can't pull a participant out. If you pull a participant out of the great chain of being, the whole thing will fall apart. Every piece is critical to the maintenance of the whole. What Cuvier was saying, well, in life, some organisms come into being and disappear permanently. They go extinct and are lost forever. Now, he wasn't arguing an evolutionary philosophy yet. Cuvier was actually rejecting an evolutionary philosophy, but he was recognizing the validity of extinction. The evolutionary ideas would begin during Cuvier's time. Around 1800, you can hang that as a date on the earliest major evolutionary ideas. One comes from an unlikely source in the form of Darwin's grandfather, Erasmus, who was a doctor. He was a physician. He wrote these prose poems, these long prose poems, many books. He was well known. This is Darwin's grandfather. And I'll let you read that on your own time. But it's in poetic form, but he's basically articulating a universal history and a history of life and a changing in organisms that was really against public opinion. The scientist working on this at the time was Lamarck, who you've all heard about in your textbooks, which are mostly wrong on Lamarck. Lamarck's set up as this bad guy, the guy who made a mistake against Darwin's insights. Lamarck was a great scientist on his own, a contemporary of Cuvier's, working at the same museum as Cuvier. And Lamarck was the first one to come up with a concrete mechanism of evolution. Erasmus may have poeticized about evolution, but Lamarck had a concrete mechanism for the process. Turns out that it probably isn't valid in the way it was framed. That's fine. It was a concrete mechanism, at least, and he deserves that credit. Well, it was the principle of use and disuse and the inheritance of acquired characteristics that together built the evolutionary process in Lamarck's ideas. And we'll look at that again when we get to Darwin on Friday. Couple final things here. Richard Owen was a comparative anatomist and a contemporary of Lamarck's and Darwin's. Owen established this distinction between homology and analogy. So wrestle with this a little bit. I'll finish with a story about my son to illustrate this, because we were out on a hike when he was little. I don't know, he was 3 or something. And we're hiking in the mountains, and it's snowy. And there's not much life out there. And he's getting bored, and he's tired of hiking. He has snowshoes on, right? And so we try to play a game, say, all right, first person to see a bird wins. And so we're all looking for a bird. My daughter's there too, and my wife. And a moth flies by from the cold tree to the next cold tree. And my son says, it's a bird. You know, I see a bird, I win. Well, it's not a bird, it's a moth, right? But it's flying, so in his mind, it's a bird. Because everything that flies is a bird, to a 3-year-old, I guess. Well, not all flying is the same, because it's done with different equipment. The flight of an insect, the flight of a bird, the flight of a bat. We'll wrestle with the concepts of homology and analogy on Friday. Have fun with your review tonight.